this episode, we're going to take a careful look at what it really means to explain a model, because a lot of confusion in data and AI starts with people using the same words to mean different things. Beginners often hear interpretability and explainability used like they are interchangeable, and it sounds like a debate that only experts care about, but it actually shapes whether your work is trusted, adopted, and used safely. A model can be accurate and still be a bad choice if nobody can understand what it is doing well enough to use it responsibly. At the same time, it is easy to overpromise by saying a model is transparent when it is not, or by giving a simple explanation that feels satisfying but is not faithful to how the model behaves. The goal here is to build a practical mindset. What kinds of explanations exist, what different people need from them, and how you set expectations so the right level of understanding is delivered without inventing certainty that does not exist. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to separate the idea of interpreting a model from the broader act of explaining it to someone else. Interpretability is about how directly a human can understand the relationship between inputs and outputs by looking at the model itself or its parameters. If you can read the model and see which inputs push the prediction up or down, and roughly by how much, that is interpretability. Explainability is wider, because it includes any method you use to help someone understand a model's behavior, even if the model is complex and not inherently easy to read. Explainability can include stories, visualizations, examples, counterexamples, and diagnostic checks, not just math. This distinction matters because some models are interpretable by design, while others require extra methods to be explainable in practice. As a beginner, you should treat these as different tools. One is about model structure, and the other is about communication and evidence. It also helps to understand that explanations can be local or global, and those are different needs that people often mix up. A global explanation is about how the model works in general, across the whole dataset, like saying which features are usually important or what patterns the model has learned overall. A local explanation is about one specific prediction, like why this one application was labeled risky or why this one transaction was flagged. Stakeholders may ask for one but actually need the other, and you can prevent confusion by clarifying which question is being asked. A manager deciding whether to deploy a model might want a global explanation that supports confidence in the approach. A customer, patient, or analyst affected by a decision usually wants a local explanation that addresses the case they care about. If you provide a global explanation when someone wants a local one, the answer feels evasive. And if you provide a local explanation when someone needs the big picture, it can feel like cherry picking. Another major idea is that explanations are not automatically the same thing as truth, and that is a hard lesson for new learners. Some explanation techniques are faithful, meaning they closely reflect what the model actually used to make its decision, while others are more like a helpful story that may not match the internal logic. People naturally prefer explanations that are simple, but simplicity can create false confidence if the real behavior is complicated or unstable. A faithful explanation might be messy, conditional, and full of trade-offs, while a neat explanation might be wrong. This is why good explainability includes honesty about limits, not just a polished narrative. In real settings, someone might push you to produce a single reason that sounds definitive, but a model can be influenced by several features at once, and the strongest driver can change from one case to another. A mature explanation often sounds like evidence-based guidance instead of a single magic cause. It is also important to recognize that there are different audiences, and they each have their own definition of what a good explanation looks like. A technical reviewer might want to understand the model class, the training data, the evaluation approach, and the failure modes, because that helps them judge reliability. A business stakeholder might want to understand whether the model supports the decision they are trying to make, what the expected benefit is, and what risks come with using it. A compliance or privacy stakeholder might focus on whether the model uses sensitive data appropriately, whether decisions can be audited, and whether outcomes could be unfair or discriminatory. End users often care about what they can do next, such as what actions could change the outcome or what the system is uncertain about. If you give everyone the same explanation, you will usually satisfy nobody. The skill is to keep the explanation consistent while tailoring the level of detail, the vocabulary, and the type of evidence to the role. One of the most common misconceptions is that interpretable models are always better, or that complex models are always unexplainable. Interpretable models have real advantages, especially for beginners, because they can be easier to debug and easier to communicate. They can also be easier to govern because you can describe what drives predictions in a way that can be checked and audited. But an interpretable model can still be misleading if the data is messy, biased, or missing important context. A simple model might look trustworthy while quietly failing for certain groups or scenarios, which can be worse than a complex model that is carefully monitored. On the other side, complex models can sometimes be explained well enough for the decision at hand, especially when you use strong evaluation, clear boundaries on intended use, and reliable explanation methods. The right choice depends on the risk of the decision, the need for accountability, and how costly mistakes would be. A practical way to talk about interpretability is to think in terms of transparency and reasoning steps. Some models are transparent because the reasoning steps map cleanly to human ideas, like a set of rules or a small number of weighted inputs. When you look at such a model, you can see the pathway from inputs to output without needing special tools. Other models behave more like a black box, where the internal reasoning is distributed and not easily summarized. For beginners, it is tempting to label black box models as unsafe by default, but that ignores context. If the decision is low risk and you can detect errors quickly, a less interpretable model might be acceptable if it performs better. If the decision affects safety, freedom, or access to critical resources, the need for transparency and accountability grows, and you should be cautious with models that cannot be meaningfully explained. Now let's connect explainability to expectations, because that is where a lot of real-world pain comes from. Stakeholders often expect a model to behave like a person, meaning they expect it to provide reasons that sound like common sense. Models do not think, and their reasons are patterns in data, which can include weird shortcuts that humans would never approve of. If you do not manage this expectation early, people can interpret model outputs as conclusions rather than predictions. A prediction is a guess based on patterns, and it comes with uncertainty, drift over time, and vulnerability to changes in the environment. Stakeholders also may expect consistency, meaning they expect similar cases to always get the same outcome. But real data includes noise, and small changes can shift a probability score across a decision threshold. A good educator approach is to explain that the model is a tool that supports decisions, not a replacement for judgment, and that its outputs must be used within the boundaries you define. A key part of explainability is deciding what question you are actually answering when you explain a prediction. People might ask why something happened, but they could mean different things, like which inputs were influential, what would need to change to get a different outcome, or whether the model is confident. Those are not the same, and answering one as if it were another can create confusion. For example, identifying influential inputs is different from recommending changes, because some inputs are not controllable, like age or history. Similarly, confidence is not the same as correctness, because a model can be confidently wrong when it encounters a new pattern it has not learned. As a beginner, you should practice framing explanations around the decision context. What is the action? What is the cost of errors? And what does the listener need in order to act responsibly? Another major theme is that explainability is closely tied to evaluation and testing, not just storytelling. If you cannot describe how the model was evaluated, what data was used, and how performance changes across different conditions, your explanation is incomplete. For many stakeholders, the most useful explanation is evidence that the model behaves reliably in the cases they care about. This is where concepts like validation, generalization, and distribution shift come into play, even if you keep the language simple. A model trained on one kind of data can behave poorly when the world changes, like when user behavior shifts, sensors degrade, or policies change. If you pretend the model's logic is fixed and timeless, you set a trap for future failures. A responsible explanation includes what the model is meant to do, what it is not meant to do, and how you will notice when it stops being trustworthy. It is also important to acknowledge that explanation methods can be misused, even with good intentions. A person can pick an explanation that makes the model look fairer, smarter, or more reliable than it really is, especially when there is pressure to deploy. Another mistake is treating an explanation method as a guarantee, like saying the explanation proves the model is unbiased, when it only describes behavior under certain conditions. Explanations can also create privacy risks if they reveal too much about individuals or training data patterns, especially when the model is used on sensitive records. In some cases, giving detailed explanations can enable gaming, where people learn how to manipulate inputs to get the outcome they want. That does not mean you should hide everything, but it does mean you should think carefully about what level of detail is appropriate for each audience. Part of stakeholder expectation management is making it clear that transparency and security sometimes pull in different directions. For beginners, one of the best ways to think about an explanation is as a contract between the model and the user. The contract says what the model is for, what inputs it relies on, what kind of outputs it produces, and what those outputs do and do not mean. It also says what happens when the model is wrong, how disputes are handled, and how often the model will be reviewed. Even if you never write a formal document, this mindset improves the quality of your explanations because it pushes you to be specific. It also helps you avoid vague claims like the model is accurate or the model is objective, which are rarely meaningful without context. A model can have high accuracy overall, while still failing badly for rare cases that matter a lot. Being clear about that up front is not weakness, it is professionalism. Another useful idea is to separate model explanation from decision explanation, because they are often confused. A model explanation describes how the model transforms inputs into a prediction. A decision explanation describes why an organization took an action, which might include the model output plus policies, thresholds, human review, and constraints. If you tell someone the model decided something, you create a misleading impression that the model has authority. In many responsible systems, the model provides a score, and a separate decision process uses that score along with rules and human oversight. That separation helps with accountability and reduces the chance that a model output becomes an unquestioned final answer. When you explain outcomes to stakeholders, it is often better to say the model provided evidence and the process used it, rather than implying the model acted like a person. This framing also makes it easier to discuss improvements, because you can adjust thresholds, add review steps, or change policies without pretending the model itself is the only lever. As you build skills for the CompTIA Data AI certification, you should also recognize that explainability is not just about pleasing stakeholders, but about building safer systems and better learning habits. When you can explain a model, you can debug it more effectively, because you can spot when it is learning the wrong pattern. When you can anticipate stakeholder expectations, you can prevent misunderstandings that lead to misuse, like treating a probability score as a diagnosis or assuming the model is equally good for every group. When you understand the difference between interpretability and explainability, you can choose models and methods that match the risk and the purpose, rather than chasing complexity for its own sake. Most importantly, you learn to treat trust as something earned through evidence, clarity, and honest limits, not as something demanded because a model is advanced. That mindset will help you on the exam and, more importantly, it will help you build AI solutions that people can use responsibly and confidently over time.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.